Hello, my name is Hussam and I'll be talking about Pneumvent, which is our team's name and as well as the name for our ventilator. And I'll be briefly going through all the functionalities as well as the mode of operation, so I'll try to go through this as concise as possible. Now, Pneumvent is a standalone unit, so you simply plug it into the main socket power supply as well as connecting it to oxygen if you have it, to a normal standard 50 psi oxygen tank or a 50 psi oxygen outlet, or you can just run it on its own, which it works by having its own pump, its own air compressor, which uses normal air as for ventilation. Now the front of it is a normal user interface panel, so you have the LCD screen here which displays information. So for instance, it's used to display the current measurement, or if you're running validation tests, it's used to display what validation tests are running at the moment, and essentially it's just a standard LCD screen. And furthermore, it also has buttons which the user or the technician can use to interact with it. Now, finally, it does have an alarm system where it simply uses this buzzer right here to send out a beep if an alarm condition is met. And if a beep is also happening, you'd normally find that LED, which is quite bright, red LED flashing. Now, if we take a look at the insides of the ventilator, it's actually quite modular. So I wouldn't say it's simple, but I'd say it's quite modular. So it works by having a battery in there, so which is a 12 volt 75 amp hour lead acid battery, which would run of course more than 180 minutes requirement. Also has a power supply and air compressor as well as the circuit board. Finally, we have the air ports in there. So this is where the pneumatic systems go in, as well as we have another air port in here, which is actually a solenoid valve. So when I say air port, it's where air enters in here and goes into a solenoid valve, which is controlled by the MCU. The most important thing in here though is the circuit board. The circuit board is where most of the operation control system and the measurement of sensors, almost everything is happening in here. So if I would give this project its whole emphasis, it will be on this circuit board. And this is simply, if I go through the circuit board block diagram, we can see that it accepts a 110 to, as actually 220 volt AC and a 12 volt battery, which will go through the power supply module, and it gets split into their voltage system. So this is where essentially you plug in the battery connector. This is where you plug in the power supply, which in turn is hooked up to the wall adapter, not wall adapter, but the wall main supply. And all of the pneumatic systems are actually electromechanical. So they have electrical wiring. So electrical wires are going to be connected in here and connected to the circuit board in here. So essentially it will be connected using wires, and then this is the main MCU which will be controlled, which was controlling everything. So it's reading the sensor data. Oh, the sensor data is actually read through the flow sensors. So we have two flow sensors, a lung pressure sensor and a tank pressure sensor, which is all is needed to run all the operations in there. Now, speaking of operations, before going in there, I will just describe that the circuit board also has an LCD unit at the back in there. So I will just, when I was describing the LCD, I didn't explicitly say that it was part of the circuit board, but everything in every electronic system is actually on a single circuit board here. So for the power modulation, the control system, the sensor data, the data acquisition, the signal conditioning, and the user interface is all in a single board. It's important to also mention we are adhering to the IEC standard for medical supplies. And the way we do this is that we isolate all the power supplies. So the main voltage system is completely isolated from the user, as well as completely isolated from the patient. Now we can take a look at the circuit diagram in here that will briefly give us an idea. I won't go into the details because it's going to take forever. However, if we take a look at the input in here, it essentially goes to battery. The battery is protected from reverse polarity. So if accidentally a technician hooks up the battery wrongly by placing the positive and the negative side, nothing is going to blow up. It's protected, nothing to worry about. And essentially what happens is that if you connect the battery to the power supply at the same time, which is the socket, precedence automatically takes place for the main power supply socket, and the battery is left in standalone so that we don't drain the charge. And we have the main MCU, which is an STM32 MCU. It's a fairly high performance MCU. It's what I think would be most suitable for this application because it's pretty much computation intensive in that you're always computing data, getting feedback and reading how much output of air is going in there, how much output of air, how much pressure is left, how much pressure is going in. So you need a high performance STM or high performance microcontroller. So my choice in here was STM32. I couldn't go with an Arduino or Raspberry Pi because these are not what I would consider rated for medical grade. A lot of things can go wrong. They're hobby grade, and I wouldn't just use it in a medical environment. And what I wanted to also mention is that we have the air valves, complete all the valves, so the solenoid valves, all the pneumatic systems in here. The pneumatic system is what I call the valve input here. This is where the pneumatic system gets open or closed. And this is just a subplate where air goes through or from the pneumatic system. Now, all of those are completely isolated also from the circuit. So whenever a microcontroller sends a signal to turn it on, it's isolated using an optocoupler, or an opto-isolator, if that's the name you prefer. And also the compressor is turned on by the MCU. So I can always vary how much air is going in from the compressor using PWM, which is another advantage of using the MCU to directly control it. Now, of course, the MCU is controlling via relay, and in order to be able to drive the 12 volt, 15 amp compressor. Now, the signaling system is quite complex. Now we're dealing with analog signals, and we have to worry about converting those analog signals to digital signals in order for it to be processed by the MCU, which is what's being done in here. So essentially, the tank pressure sensor is what's referred to as the mixture. I mentioned tank in here, and what I mean by tank is the total mixture of oxygen as well as the total mixture of air combined at the same time. So this pressure in here is actually converted using it's actually converted to a digital signal, but before that we have to actually do what's known as analog signal conditioning, which is converting those differential signal into a single output signal. So it's done using an instrumentation amplifier. And essentially this happens to both the tank pressure and the lung pressure because these are differential outputs. We are lucky that I was able to source a digital output differential flow sensors. And the reason I chose a differential flow sensors is because I want to measure how much air is going into from the lungs, and I want to measure how much air is coming out. And the way I do this is essentially using a flow sensor. So after doing this, we have to consider the alarm conditions. So there are situations where an alarm needs to be triggered. So I described this more in details in the validation test and the validation testing methods. So if I open the document in here, so these are the conditions in which most likely a fault is going to occur. And for instance, if the lung pressure suddenly drops low, or a breath hasn't taken in a certain time, an alarm signal is going to be triggered, and essentially the MCU is gonna be driving the LED here, and the buzzer that I talked about earlier. Now, finally, the final part of the electronic system is the human-machine interface. So as I described, so we have 6 buttons. Each button has a dedicated purpose. I described the purpose of these buttons in the documentation, so I won't go them in this conversation because I think it's going to take a lot of time. However, it's very intuitive. If you go through the documents, the LCD is controlled by the MCU, and it runs on a 2 kilohertz oscillator, so the LCD actually needs an external oscillator to properly run. However, once it's hooked up into the MCU, which is pretty straightforward, essentially what you do is you get the LCD system and solder it to the pins in here. So these pins in here are for the LCD on the back side, so the LCDs just slide in there and it gets soldered through. All of this is taken care of during the manufacturing process at my facility, so we don't have to worry about how is this going to be produced, how feasible is this, because we are taking care of the production of this. Now, if we take a look at the assembly system from outside, so how a nurse or a technician is going to hook up the system, we are using a breathing tube with two tubes, one for inspiration, one for expiration, which is connected from this end to the pneumatic system that I showed earlier in here, using an adapter. So it connects in there. And finally, secondly, we connect it to a heat and moisture exchanger and filter. And then it connects to a double swivel elbow. So essentially this is what it looks like in the end. And we can actually turn this double swivel. We have another option to turn into a straight swivel elbow. And this is how the system is going to be hooked up. So the patient essentially is tubed in here and is going to go through a system in here. This tube in here, the small tube in here, goes to the flow sensor. And everything will be essentially modular at this stage, so everything can be taken care of. You want to clean this, you want to remove this after each patient, you simply have to disconnect these and throw them in the garbage, or whatever sterilization method a hospital might probably use. But this is what I would consider as a hygienic standard in order to be replaced. Now, if we take a look at the pneumatic system, I went through it. I just want to mention that we have this document describes how the system is connected from a pneumatic point of view. And we have a Y connector in here that essentially combines the oxygen and combines the air compressor air. And this is always regulated. So I can always control how much air is flowing into the Y tube as well as how much oxygen using the MCU, because I am always in constant feedback of how much pressure I'm allowing to go through and how much pressure I can tolerate.